Hi there. Today we're going to discuss a very critical skill in chemistry as well as the underlying concepts. We're going to be looking at electron configurations and orbital diagrams. So in order to do this, we're first going to go over some of the underlying rules of electron structure, followed by a discussion of how to write electron configurations as well as how to draw orbital diagrams. We're then going to discuss how to abbreviate these with a noble gas configuration, discuss what happens when atoms become ions, and discuss how electrons can become excited. Finally, we're going to wrap it up with a quick conversation about magnetism and how it relates to the electron structure in atoms. So first of all, I want you to remember from the quantum model that electrons are organized within energy levels, which help to explain the distance or relative distance they are away from the nucleus, as well as their relative energies. Followed by energy levels, electrons are then arranged in sublevels, and finally in orbitals. Electron configurations are written representations of each electron within an atom. They show the energy level as well as the sublevel on which each electron exists within that atom. We're going to continue to refer to the energy level as the variable n. Now, orbital diagrams are a bit different in that they're going to show not just the energy level and the sublevel, but also they're going to show the specific orbital in which each electron exists. In order to understand how to write electron configurations, we must know how electrons are added sequentially to an atom. First of all, electrons are going to seek out the lowest possible energy state, as this is the most stable state. This means that electrons will be added to the lowest energy first, before being added to the higher energy states. This is known as the Aufbau principle. Now, Aufbau in German actually means bottom up, and in this case, we're going to be building from the bottom up. Next, remember that each orbital can only hold 2 electrons, and the Pauli exclusion principle, our second rule, states that these 2 electrons within a single orbital must spin in opposite directions in order to maintain stability. Finally, electrons inherently repel each other, which means that they are more stable alone than they are with a partner. The final rule is Hund's rule, which is also known as the empty seat rule. Much like on a bus where you'd rather sit alone than with a stranger, electrons would rather enter an orbital by themselves as opposed to pairing up. Now, once each seat or orbital is half filled with 1 electron, then the second electron can be added to each one. So let's take a look at how we're going to diagram both electron configurations and orbital diagrams using our example of hydrogen. Now, hydrogen has only 1 electron, and that's going to be held within the s sublevel on the first energy level. We're going to refer to this in the future as the 1s sublevel. To write the electron configuration, we're going to write the energy level, then the sublevel, then as a superscript, the number of electrons held within that sublevel. For hydrogen, because there's only 1 electron, it would be written as 1s1. Now for the orbital diagram on the bottom, we're going to show the electrons as arrows. Remember how we said that paired electrons need opposite spins? Well, we're going to show these opposing spins as up-facing and downward-facing arrows. For each orbital, the first electron being added is going to point up. So in hydrogen, we show the orbital diagram as just a single upward-pointing arrow in the 1s orbital. Alright, so let's go ahead and build the next atom. Helium has 2 electrons, both of which are held within the 1s sublevel. For the electron configuration, we're going to write it as 1s2 in order to show the second electron within that first s sublevel. On the orbital diagram down below, notice how we've added the second electron with a downward-facing arrow, signifying that it has the opposite spin of the first electron that we added. Remember, this is the Pauli exclusion principle in action. Moving on to lithium, we're going to actually need to reach into the next energy level with the third electron. Notice how we've written this in the electron configuration. We write 1s2 representing the first 2 electrons, and then 2s1 representing that final electron. In the orbital diagram, we're going to show the electron being added to the 2s orbital with an upward-facing arrow. Beryllium adds 1 more electron to the 2s sublevel, which you can see here as 1s2, then 2s2. You You can also see the new electron being added with a downward spin in the orbital diagram. In boron, we're going to need to reach into a whole new sublevel within the second energy level. This is going to be the 2p sublevel. Now the electron configuration for boron is going to be 1s2, 2s2, then 2p1, showing that both the 1s and 2s sublevels are full, and that there is one electron within the 2p sublevel. In the orbital diagram, we're going to actually have to show all three possible p sublevel orbitals, but we're only going to have the one electron in the furthest left orbital. It's going to have an upward spin. In carbon, we're going to add another electron to the p sublevel, but remember, in this case, that electron must be added to the second orbital, because orbitals can only gain one electron first before gaining the second. So do you remember the rule that stated that? That's right, it's the empty seat, or Hund's rule, that states that. So here we can see that the second electron ends up in the second 2p orbital. It also has an upward facing spin, or an upward facing arrow. In nitrogen, we're going to add the next electron to the third 2p orbital, as you can see down in our orbital diagram, and our new configuration for nitrogen will be 1s2, 2s2, 2p3. So now our p sublevel is half filled. The last example we're going to be doing is oxygen. So in oxygen, we have to add one more electron than we had in nitrogen, but in this case, because all three of our 2p sublevels already have one electron, we're going to have to add the next electron to the first 2p orbital, and we're going to add it with a downward facing arrow. That's going to show our opposite spin of this next electron. So in each of these, we're going to be able to continue to build and build electrons, and we can build any atom on the periodic table using this same technique. In fact, there's a really common table that's going to show exactly how sublevels fill. Notice how we have written all 7 energy levels of the S sublevel from 1 to 7. There's no 1p sublevel, so we start with 2p. This is going to go next to the 2s. Similarly, there's no 1 or 2 D sublevel, so we're going to start with a third energy level of D. For F, we start with 4. Now, we can actually go even further down than the 7, but so far there are no known elements beyond that 7th energy level. On the right, you can see that we have a diagram which shows each sublevel in a slightly different way. This shows the relative energy of each sublevel. This diagram goes a bit further because it also shows each orbital within the sublevels as a dot. The lower on the diagram, the lower the energy of the sublevel, and the higher on the diagram represents a higher energy sublevel. Remember, this is going to relate to our Aufbau principle, which states that electrons are going to fill from low energy to high energy. So remembering back to the examples we just did, the 1s sublevel is going to fill first. Notice how I've written the configuration up top, as well as with the 1s2, representing that 2 electrons fit within that 1s sublevel. Next comes our 2s sublevel with 2 more electrons, then 2p with 3 orbitals, and therefore 6 electrons, followed by 3s with 2 more electrons, then the 3p sublevel with 6 electrons, and the 4s sublevel with 2 more electrons. This is where things are going to get a bit odd. Notice how when we continue that pattern on the left diagram of diagonal arrows, or if we were to go on the right diagram and go up one more level, we're going to end up hitting the 3d sublevel before we actually reach the 4p sublevel. So the reason for that is because the 3d sublevel is actually of higher energy than the 4s sublevel, but of less energy than the 4p sublevel. This is largely due to the fact that electrons repel each other, and so having that many electrons is going to have more repulsion, so a little bit of higher energy. Therefore, what's going to happen is it's actually going to fill in between the two. In fact, every D sublevel fills after the S sublevel that is 1 energy level higher. This means that the D sublevel is always going to be 1 energy level lower than both the S and P sublevels that surround it. Also, remember that the D sublevel contains a total of 5 orbitals, which means 10 electrons. After the 4p fills, the 5s sublevel fills, followed by 4d, then 5p, then 6s. We end up hitting another snag as we reach the F sublevel. Now, again, due to electron repulsion forces, the F sublevel is of even higher energy and fills after the S sublevel 2 energy levels above it. This means that the 4F sublevel does not actually fill until after the 6S sublevel. This means that the F sublevel is almost 2 energy levels lower than both the S and P sublevels that surround it, and it's going to be 1 energy level lower than the D sublevel that's adjacent to it. So we're going to fill the 4F sublevel, followed by the 5D sublevel, then the 6P sublevel, and the 7S sublevel. Finally, we're going to fill the 5F, 6D, and 7P sublevels. Now, as I stated earlier, this pattern could theoretically continue to infinity, but we're going to reach a point where an atom is going to be so unstable that it would likely never exist and electrons would be immediately ejected from the atom as opposed to existing at these higher energy levels. At this point, you might be saying to yourself, wow, if I were to diagram a really big atom like uranium, this could get ridiculous. Well, fortunately, there's an abbreviation we can use known as the noble gas configuration. The noble gas configuration allows you to only write the final row of the configuration starting with the S sublevel. We start by placing the symbol for the most recent noble gas in brackets, and then write the electron configuration just as we would from that point on. For example, in sodium, the most recent noble gas is neon, so we put neon's atomic symbol in brackets, followed by 3s1, which is the electron configuration for sodium that follows neon. For silicon, neon is still the most recent noble gas, but now we have to add a bit more to represent the electrons beyond neon. So as you can see with silicon, we end up with brackets around neon, followed by the 3s2, and then 3p2. In addition to having to write the electron configurations for neutral atoms, you're probably going to be asked to show the configurations for ions as well. In this case, it's going to be as simple as writing the electron configuration, but removing the outermost electrons for cations, or adding outermost electrons for anions. So for sodium, which has an ionic charge of +1, we're going to lose the electron from the outermost energy level, which in this case is the 3s electron. The resulting configuration is going to be isoelectric to neon, and is going to read 1s2, 2s2, 2p6. Tin represents why you cannot simply remove the last electrons that are written in the electron configuration. So remember what I said in the last slide. We're going to remove the electron on the highest energy level, or the outermost electrons. For that reason, when we write the electron configuration for the tin +4 ion, we've removed electrons from the 5p and 5s sublevels because they're further away from the nucleus than those that are in the 4d sublevel. So notice the ionic configuration for tin is going to be noble gas argon followed by 4d10. So applying that to iron, for the iron 3+ ion, we're going to remove 3 electrons. The first 2 electrons removed come from the 4s sublevel because they were at the highest energy level, so the furthest to the outside of the atom, followed by 1 electron coming off of the 3d sublevel. This is going to result in a argon noble gas, followed by 3d5 electron configuration. A set of common terms you're going to hear thrown around is going to be ground state and excited state. So what are these? Well, the ground state configuration of an atom means that the Aufbau principle is followed completely. This means that every electron in the atom is at its lowest possible energy configuration. Excited state, meanwhile, means that there's at least 1 electron that's in a higher energy level than it should be. In order for this to happen, energy has to be added to cause the electron to jump to a higher energy. Hence, it's excited. Notice how it changes both the electron configuration and the orbital diagram so the lower sublevels are not full before the higher sublevels fill. You might be expected to look at an energy diagram or an electron configuration or an orbital diagram and identify one that is or is not at an excited state. The final concept we're going to discuss today is magnetism. Now, magnetism is actually related to electron configuration in that magnetism is caused by unpaired electrons. There are two major terms that you need to be aware of. The first is diamagnetic, and diamagnetic means that all electrons are paired, such as here in the neon atom. Secondly, paramagnetic means that there are unpaired electrons present, such as here in oxygen. The more unpaired electrons, the more magnetic the atom or ion is going to be. So that wraps up this video. Let's do a quick recap. We started by discussing the three major rules of electron structure, followed by a tutorial on writing electron configurations and drawing orbital diagrams. We then abbreviated the electron configurations using noble gas configurations and discussed how to diagram ions. Finally, we discussed ground state versus excited state electrons and how electron configurations are related to magnetism.